If you spent just 1 hour orbiting close enough to a black hole, everyone you have ever loved would be 7 years older by the time you returned. Your coffee would still be warm. Their lives would be unrecognizable. This is not science fiction. This is a confirmed, measured, mathematically ironclad consequence of Einstein's general theory of relativity. And the most unsettling part is not that time slows down near extreme gravity. It is that from your perspective, inside that orbit, absolutely nothing would feel different. You would feel no strange sensation, no warning, no signal. Time would simply be quietly stolen from the people waiting for you back on Earth. In 1971, physicists Joseph Haffel and Richard Keating placed atomic clocks aboard commercial airplanes and flew them around the world. When the airborne clocks were compared to identical clocks that stayed on the ground, they measured a real physical difference in elapsed time. The clocks on the plane, moving faster and sitting at higher altitude, had recorded slightly different amounts of time than the ones on Earth. The difference was tiny, measured in nanoseconds. But it was real. It was measurable. It was undeniable. If a commercial airplane flying at ordinary altitude can produce measurable time dilation, imagine what happens at the edge of a black hole, where gravity becomes so intense that not even light can escape. To understand what is really happening, we need to talk about what time actually is. Most of us think of time as a universal clock, ticking at the same rate everywhere in the universe. Einstein shattered that assumption completely. In his framework, space and time are woven together into a single fabric called spacetime. And massive objects warp that fabric the way a bowling ball warps a stretched rubber sheet. The more massive the object, the deeper the warp. And here's the key insight. Clocks tick slower in regions where spacetime is more deeply curved. This is called gravitational time dilation. Now scale this up to a stellar mass black hole. We are talking about an object that packs the mass of several suns into a region smaller than a city. The gravitational field around it does not just warp spacetime a little. It bends it so severely that time near the event horizon, the point of no return, runs at a fraction of the rate it does far away in open space. If you were orbiting at a safe but dangerously close distance, perhaps just outside the innermost stable circular orbit, time for you could slow to a crawl relative to an observer watching from Earth. Scientists and physicists have calculated what this would actually look like using the Kerr metric, which describes the geometry of spacetime around a rotating black hole. For a maximally spinning black hole, which is what the movie Interstellar was actually based on, an astronaut orbiting at the innermost stable orbit could experience time dilation ratios where 1 hour of their time corresponds to roughly 7 years of Earth time. This is not approximation. This is derived directly from the equations of general relativity, the same equations that predicted gravitational waves decades before we could detect them. The same equations that GPS satellites must account for every single second, or your navigation would be off by kilometers per day. If you are finding this as mind-bending as I am, do me a favor right now and hit that subscribe button and ring the notification bell. Every week, we go deeper into the science that makes reality stranger than any story we could invent. Now, here is where it gets truly existential. Imagine you are the astronaut. You launch from Earth, you complete your 1 hour orbit, and you return. From your perspective, 60 minutes passed. Maybe you listened to a playlist. Maybe you ate a meal. But when you dock and open the airlock, the colleagues who watched you launch are now 7 years older. Children you left behind are in a different grade in school. Technology has moved forward. Political leaders have changed. The world you left is gone, replaced by a world that looks the same but carries 7 years of history you completely missed. And you cannot go back and reclaim those years. Time dilation only runs one way. You can never return to the moment you left. You can only arrive in a future that moved on without you. The physics gets even stranger when you approach the event horizon itself. At the event horizon, time dilation becomes infinite from an outside observer's perspective. If someone on Earth watched you fall toward a black hole with a powerful enough telescope, they would never actually see you cross the horizon. You would appear to freeze, your image growing dimmer and redder as your light becomes increasingly stretched, until you fade from view entirely. Meanwhile, From your own frame of reference, you would cross the event horizon in a perfectly finite and unremarkable amount of time. Two entirely valid perspectives of the same event, producing two entirely contradictory experiences. Both are correct. Neither can communicate their truth to the other. This is the part that mainstream coverage almost always glosses over. Time dilation is not just a quirky relativistic trick. It is evidence that time itself is not a universal background condition. It is a local, physical, measurable property that changes depending on where you are and how fast you are moving. Your time and my time are only approximately synchronized because we happen to live at similar depths in Earth's gravitational field and move at similar speeds. Change either of those conditions dramatically, and our clocks diverge permanently and irreversibly. We have already confirmed this at small scales. The GPS network corrects for time dilation every single day, accounting for both the velocity of the satellites and their position in Earth's weaker gravitational field at altitude. Without those corrections, the entire system would drift into uselessness within hours. We are already engineering around time dilation because reality demands it. The black hole scenario simply takes these confirmed, everyday physics and amplifies them to their most dramatic and philosophically staggering conclusion. 1 hour, 7 years, your coffee still warm, their lives irreversibly changed. If this reshaped how you think about time, share this video with someone who still thinks time is simple. And subscribe because next time we are asking something even more unsettling. If gravity can slow time, what happens to time at the exact center of a black hole where gravity becomes mathematically infinite? Does time stop completely, or does something far stranger happen instead?